This is PS1, Chapter 1, Part 2 on the nature of science. In this portion of the video lecture, we will continue our discussion on scientific methods, and we will also take a look at standards of measurement and graphs in science. In some cases, scientists cannot always directly observe for their experiments or investigations. For example, if you are a scientist that studies space systems, it is very difficult and I would say impossible to hop on a spaceship, on a rocket, and go to the nearest star outside of our solar system, for example, Proxima Centauri, and study that star. So things cannot always be directly observed. So in those cases where scientists don't have that direct access, they can develop a model. A model can be an idea, it can be an event, or even an object that's used to represent their observations. When we talk about the scientific method, inevitably, the discussion of scientific theories and laws will come into play. They are two separate things. Sometimes they're used interchangeably, although that's not correct. So we're going to dispel some of the myths of scientific theories and scientific laws. A scientific theory is not a guess. The word theory indicates that perhaps a scientist is just making something up so it sounds good, or so maybe it fits what they want to have for their results. But a scientific theory is an explanation based on several observations, usually done by many different scientists in the same field. And their theories are also supported with many investigations. Remember, good science is repeatable science. And if science investigations are giving the same results over and over and over again, you can develop a scientific theory. Again, it's evidence that supports the most logical explanation for the answer to your question. Theories can be modified. There are theories that we have had throughout science that no longer exist because we found out more and new information. For example, in biology, there is the theory of spontaneous generation. That theory stated that life could come from non-living things. So if you had a pond in your backyard and a creek that would enter into the pond, there were fish in your pond. According to the theory of spontaneous generation, the fish were there because the mud itself from the bottom of the pond birthed the fish eggs, and then the fish eggs hatched and became adult fish. We know now through the theory of biogenesis that only life can produce living things. So again, theories can be modified. The theory of evolution in science is one that is constantly modified based on new observations and research that's being done. So we can get new information and make the theories better. We can also get new information and throw those old theories out the window. Now, scientific law is very different than a scientific theory. A scientific law is a statement about what happens in nature, and that seems to be true all of the time. So laws explain the what of something. For example, the law of gravity. There is no possible way, given a normal situation, if you were to hold an apple in your hand, if you were to let go of that apple and let it fall, that's due to gravity. If you let go of the apple and it hovers there in space, that will be a violation of that law, okay? That's not going to happen in nature. That's not going to happen in the natural world. Things will fall towards the center of the earth due to gravity. So laws explain the what. Theories give a possible explanation for the how or the why. So for the why do different animals look the way they do? Well, that's explained by the theory of evolution by natural selection. Okay, the law of gravity is explaining what happens when you let go of something. Okay, limitations of science. We can't use science to explain or solve everything. Science is not the end-all be-all for every answer that you will ever want to have in your life. Remember, science is limited to the natural and physical world. We can't, for example, take a piece of music or a work of art and scientifically take a look at that and analyze it, for example, for beauty. Okay, some people are going to like the piece of music and think that it's beautiful. Others may not like the work of art as well. Some people may really like this work of work, and then others may think, well, you know, that's really not me. You can't place science on everything, so there are limitations. One of the benefits of science and using science is technology. Technology is the application of science to help people. So we use what we know, the background, the science part, and we apply that to different problems in our lives with technology to make our lives better or more efficient. So technology is the application of science. Science and technology don't always produce positive results. When Henry Ford put out the first cars on the very first roads, never in a million years, I would imagine, did Henry Ford think that families in the 21st century would have multiple cars, and then we would need an entire system across the country of roads. Also was not aware of a little thing called carbon dioxide emissions from the burning of the fossil fuels in the gas. So we have a little bit of global CO2 rising levels because, in part, due to the burning of fossil fuels, and cars are a big contributor to that. So science and technology don't always produce positive results. In some cases, I believe that scientists and engineers try their best to get positive results, but it's not always going to happen. Standards of measurement in science. When we perform experiments as scientists, it's very important to use units and standards. So a standard is an exact quantity that people agree to use to compare measurements. That way, it doesn't matter if a scientist is Russian or Chinese or African. They can all interpret the same information from measurements. It's kind of a universal language, the standards of measurement in science. When we take a look at measuring things, we have to take a look at two different aspects. Again, a lot of people use precision and accuracy to mean the same thing, but they do not. Precision is how carefully you make your measurements. And accuracy is going to compare your measurement to an already accepted value. So as you can see from the graphic here, you can be both precise and accurate by having all of your darts hit the middle of the dartboard. You can be accurate and imprecise. So you can be fairly close to the middle, which is our accepted value of the best for darts, but not have have a random grouping of your darts. Now, you can be inaccurate by not getting all of your darts close to the center, which would be our standard value, but you can get them all grouped together. So you can be inaccurate and precise. So precise is getting them to group fairly close together, but far away from the center. And then what you have to remember with getting involved with biases, you don't want to be inaccurate and imprecise, because then your measurements are really, really off. So for standard measurements, we use the metric system or the international system of units. So SI are standards that are universally accepted and understood worldwide. So these graphics are from your textbook, so we can take a look at length and mass and time, mostly for our purposes in Physical Science 1, and we have standards and symbols for that. So no more English system. So no more inches and feet and yards. Okay, we're going to be in miles and pints and acres. Okay, so we're going to keep it clean and keep it metric. So meters, liters, and grams. And the type and size of the unit used will depend on what is being measured. The SI system of measurement, or the metric system of measurement, is very easy to use. It's easier than the English system of measurement because the metric system of measurement is based off of units of 10. So it's very easy to convert from one point to another using the metric system. Now, in our experiments, a lot of times scientists will have results that they need to display visually. Lots of times we're going to be working with graphs in science. So a graph is a visual display of information or data. It makes it very easy to understand complex patterns when these things are put into a graph. It's a very quick visual way to understand results of an experiment. There are many different types of graphs, but all graphs need to both be accurate and precise. So in most cases, most of the graphs that we will be dealing with here in physical science, and science in general, would be the line graph. Line graph is going to be your dependent variable changing due to a change in the independent variable. So this is going to be a line graph, is what I like to call a this or that graph. So you're going to be taking a look and comparing two different things to see how one makes a reaction with the other. A bar graph compares information collected by counting. And a circle graph will show you how some fixed quantity is broken down into parts. Again, in most cases, we will be working with line graphs and bar graphs in this class. It is very important for you to note that all graphs for all labs, all activities, all assignments in this class will have your name, block, and date on it. You have to title your graph. You have to give it some type of title so people that are looking at it can know what the graph means. You have to label your axes with correct units. Remember, SI or metric system units only. If you are graphing more than one line on your graph, for example, you will need a key to tell me what line, what color means what in your graph. All graphs have to be neat and precise and accurate. They have to be on graph paper, and you need to use rulers, and they need to be as large as possible. Teeny tiny graphs make for very difficult analyzation and interpretation of those graphs. And because graphs are a very easy visual way to see what's been done in your experiment, they have to be both, again, accurate and precise. This has been Physical Science 1, Chapter 1, Part 2 on methods of or nature of science.